Okay, so let's continue from where we left off. So we just finished talking about something called the Church-Turing thesis, which essentially says that our notion of algorithms are equivalent to Turing machines. So we've been talking about Turing machines for several lectures now, and our notion of what an algorithm is on a realistic computer is computationally equivalent to a Turing machine. And we saw justification of why that's true last time, that a computer can simulate a Turing machine just by writing a function to actually keep track of the tape contents, like in Python or something. And a Turing machine can simulate a computer by just simulating the basic operations that a computer usually does, like addition, multiplication, division, all that stuff. And every single function that a computer can do, a Turing machine could do. So this is what we have established here. And for that reason, we can note here that if a Turing machine cannot solve a problem, then neither can a computer. So neither can and I don't have a precise definition of what a computer is, but our intuitive idea of what a computer is. Okay, so one way to actually ask this, well, are there actually such problems? So are there any such problems that cannot be solved? So, and if there are, well, how do you actually show that a Turing machine cannot solve a problem? There's no decider for it. So that's what we mean by solve here. So solve means there is no decider for a given language L. So if I want to show that a Turing machine cannot solve L, what that means is that there's no decider for that language L. There may be a recognizer for it, or there might not even be that. But by solve here, I mean there's no decider for it. And the way that we're going to actually go about doing this is to understand why there can't be a decider for certain languages. What we're going to do is we're going to go through the opposite viewpoint, but to talk about instead which problems could Turing machines actually solve. So by understanding what problems Turing machines can solve, we can actually get a better grasp of problems that Turing machines can't solve. So we've done this exact same thing with regular languages and context-free languages. We looked at the ones that were in those classes to get a better sense of ones that are not in those classes. So it's the same idea here. And thankfully, there's no pumping lemma for decidable languages or something. And I'm doubtful that there even is one. So we're not going to talk about that. But instead, what we're going to do is, well, let's revisit that question, that statement I said earlier, that a computer can simulate a Turing machine. And this is pretty obvious, but let's actually think about this a little more. Well, this essentially is just saying, well, a Turing machine can be represented on a computer by a string. So it represents a Turing machine as a string of zeros and ones, but we can think of it like a string of characters or something. So maybe, for example, we have maybe the representation looks like this, but it may be different than this, but this is one possibility. So maybe we put the states as a list, and so these pound signs are delimiters. Then maybe the input alphabet, then the tape alphabet. Then what else do we need? So we need the start state, then the accept state, and then After that, we need the reject state. So then maybe we just have something like this, where this is a gigantic string that's representing what a Turing machine actually is. So we're going to actually try to generalize this to all classes of machines. So, and then what we could try to understand about a Turing machine is, can it answer questions about other machines? Because computers can answer questions about what Turing machines can do. Well, can Turing machines, or I guess even computers because they're equivalent, could it answer questions about DFAs, for example? And the reason we're doing that is we're going to build up to Turing machines, which will allow us to show that a problem can't be solved by looking at ones that can be solved by answering questions about other machines. So that's how we're going to do it. So the way that we're going to do this is, let's just say that we have some kind of machine M. So this could be a DFA, NFA, and I'm going to put this in quotes because it's not really a machine. It could be a CFG, a PDA, and anything like, or a Turing machine or anything. And what we're going to do is going to represent it like this. So angle brackets with the machine's name on the inside. So what this is representing is the string encoding of M. And encoding just means string representation. So it's exactly this string over here. So the example that we gave is one possible encoding of the machine. Maybe we flip-flop the order of the things in the list. Maybe we don't have delimiters or something like that. So as long as we could, once we're given the string, if we could actually determine what the machine actually is in a finite amount of time, then that's all we actually need. So here is the first problem that we're going to look at. It's called A sub DFA. And so what does this mean? Well, the DFA should be pretty clear what it's referring to. But the A here is called the acceptance problem, quote unquote. And so what is this language? So again, like all languages, it's just a set of strings. That's all it is. And what these strings are is this. Is M comma W, and I'll explain what that is in a second, where M is a DFA. So M without the angle brackets is just the machine itself, not the string. So the machine itself is a DFA, and the string here, the W string, is in the language of M. So what is this angle bracket MW thing? So this is some encoding of a DFA M and a string W. So it's not just the machine, but somehow we're fitting another string into the mix, and we're writing this out as a string. So maybe in the example above, we put like W1, W2 up to WN as the string W. That could be one way that we can encode it. I don't care what the encoding actually is, as long as we can determine what the machine actually is once we receive the string. So, of course, these are string encodings, so it's just a set of strings. And one way that we should always be thinking about languages like this is, at a high level, what we should be doing is we're given M and W, so we're given that string, and we want to determine whether or not that thing that we're given, that string, is inside A sub DFA. And in fact, that's literally the entire class, what we've been doing so far. We're given a string, and we want to check it whether it's in a language or not. And and if it's not in the language, we want to determine that also. So it's exactly the same idea here, but we can think about this in terms of given a machine and a string, and then what we can do with that. So what I'm going to claim here is that A sub dfa is decidable. So recall that decidable means a Turing machine exists for A sub dfa that always halts. Okay, so if we're going to show that this is decidable, I better give a machine that always halts and never ever runs forever. So here's how we're going to do that. Well, if you're a computer and you wanted to simulate a DFA on an input, what would you do? What you would do is just run the machine on the input and then just see what happens. Because if you have n characters in the string, you will just execute n transitions and then you just observe the state that you're in. So I'm going to make a decider D. So this is the decider that we're going to make. And so here we're always going to exclusively work with high-level descriptions of machines. We're never going to do low-level or anything. So on input MW, and we should always be clarifying what M and W represent, because this could be representing some other machine and input or something. So where M is a DFA and W a string. I don't know whether or not at this point W is in the language of M yet, but I know it's a string at this point. So the first step is to run M on W. And then, just as we just talked about, if M ends the computation in a final state, except. Because here we're talking about the A sub DFA problem. So remember, we're trying to make a decider, which always says accept yes or reject no. So if the DFA that we're given on this input W ends in a final state, well, that means that M does accept W. Well, that tells us that the string MW should be in A sub DFA because M accepts W. W is in the language of M. So therefore, we should say accept here because we have determined that M accepts W. And then otherwise, if it doesn't end in a final state, well, that means that W is not accepted by the machine, which means we should reject. And that's the whole machine. So the justification is pretty clear. We just run the machine on the input, and if we end in a final state, we say yes, the machine accepts the input. Otherwise, we reject the string MW because we determine M does not accept W. So the only justification we need here is this actually a decider? So this first step runs in a finite amount of time because, well, the string W is of finite length. We don't have an infinite length string here. And M is a finite length description of a Turing machine. So written on the tape, there's the part that contains the machine M and the part that contains the string W. Well, then the machine will have to zigzag back and forth to determine what state we're in, what character we're reading next, and look up in the transition function of the DFA, but that can all be done in a finite amount of time because both M and W are finite in length. And this last part runs in a finite amount of time because all that we need to check is, well, the state that I'm currently in, that I'm maintaining, what state I'm in, I just look up in the description of M what state I actually ended up in and whether or not it's a final state. So I just look through the final states of M and I see whether or not the state I ended up in is one of those states. If it is one of them, then I accept. Otherwise, I don't. I reject at that point. And so, therefore, both of these steps run in a finite amount of time. And so I accept or reject in a finite amount of time. So this tells us that D is a decider for A sub DFA. And so now we have shown a decider exists, so therefore A sub DFA is decidable. And one minor nitpick. So always try to remember that a language is decidable and a machine is a decider. It's not possible for a language like A sub DFA to be a decider. So some people I've seen write, run the decider A sub DFA. So you could say run the decider for A sub DFA because the language can never be a decider, is always decidable by some decider. Okay, with that out of the way, let's talk about the next level up. So we're going to look at the exact same type of question, but instead we're going to talk about NFAs instead of a DFA. So here M is an NFA and W is a string in the language of the machine. It's accepted by the NFA. And I claim that this is decidable too. So again, we gotta show some machine that runs in a finite amount of time and always gives the correct answer. So how do we actually show this? So we could just try to do the previous strategy of just running the NFA on that string W, but a problem here is that there could be a loop of epsilon transitions, so something like this. And it could be that the Turing machine, well, it has to make a choice, first of all, and the Turing machine has to be deterministic. But even setting that aside, if it happened to make the choice of taking these epsilon transitions, it will run forever. But we have that famous result of converting the NFA to a DFA, and based on what we just did, we know how to answer the question for DFAs. And why is that relevant? Well, the conversion converts the NFA into an equivalent DFA. And so we can just forward the answer to the work we just did. We don't have to revisit all of the work we did before. Let's just build on what we've already done. So let's make a decider for A sub NFA. So on input MW, where M is an NFA and W a string. So the first step is let's convert M into an equivalent DFA I'm going to call D. And let's run the decider for A sub DFA on some input. Well, we got to give it a string, so it's going to be some encoding of a machine in a string. Well, here, A sub DFA is expecting a DFA and a string. Well, we got a DFA right here, so the DFA has to go in, and then the string happens to be the exact same string because I want to output the same answer. So in this case, it's W. So one of the major hiccups that students make is what to actually put in these run the decider on some input. Some students have a lot of problem trying to sort out which machine and input to actually send in here. So the thing that you should always remember is A sub DFA is expecting a DFA and an input. It's not expecting anything else. So you can't just send in an NFA or a CFG or whatever. It has to have the right type of input. And then once you have the right type of input, you should try to understand why you're actually sending it into this decider. Well, in this case, we converted it to a DFA, and so because we want to forward the work onto the decider for A sub DFA. So then all we do here is output whatever the technical term the decider says, because we want to output the exact same answer that the A sub DFA, the decider for A sub DFA says, because we converted it to an equivalent DFA. Well, steps 2 and 3 are pretty easily shown to run in a finite amount of time because we made a decider, so it can't run forever. And step 3 obviously takes a finite amount of time. Step 1, well, that takes a finite amount of time because if I had n states for the NFA, I only have 2 to the n states for the DFA. A lot of states, but still only a finite number. So each of these runs in a finite amount of time. So, what we can deduce from this is that A sub NFA is decidable. Pretty cool. So now let's work our way up one level. So I'm not going to go through the entire kit and caboodle for this, but we're going to do one right here for regular expressions. So R is a regex, and so this is the notation that they use. X is the string that they input for a regex, not input, but is described by the regex, I mean. I don't know why they don't use W. It's just what they're used to, I guess. And the idea here is to show that this is decidable, to convert to an NFA, which takes a finite amount of time, and then ask the A sub NFA decider, the decider for A sub NFA. And then, well, A sub NFA's decider runs in a finite amount of time, and the conversion to an NFA runs in a finite amount of time. So this tells us that A sub rex is decidable. Okay, cool. And we could answer the exact same question, although I won't do it here, for regular grammars. So where M is a regular grammar, and we could do the exact same thing, and that's decidable too, because you could just convert it to an NFA and then appeal to the decider for A sub NFA. Okay, so let's switch gears a little bit. So let's start talking about a different class of problems. So these A problems are the acceptance problems, as I said before. But there's a different class of problems, one of 3 main ones that we're going to see. And this one is the E class of problems. So the E here stands for the emptiness problem. So what is this? So again, it's a language, no difference there. But here, instead of a machine and a string, what you're going to get is a single machine and nothing else. So no inputs here. And here again, as you might expect, M is a DFA. And here, we're going to have the language of that machine be empty. So what does that mean? That says that the machine M does not accept any string whatsoever. Okay, so it basically just is a test of whether the DFA really does anything, whether it accepts anything. So uh, you may think, well, how do we actually solve this problem? Well, let's see. Well, let's just say that we have a start state right here. If there's a set of transitions that allow us to get to a final state somewhere, then we can just read off the characters on the transitions, and well, that's a string that is accepted. But if there is no such link between the start state and a final state, then it can't be that the machine accepts anything, because there's no way to like jump to a supposed final state. So a lot of students get this problem wrong in the sense that they just say, well, just test whether or not the DFA has a final state. If the DFA has no final states, well, it can't accept anything, and that's true. But a simple counterexample to this would be this one. So let's just say we have a start state that loops on everything, but then we have a lone state out here that loops on everything that's a final state. And I call this my DFA. Well, there is a final state, but it's just not reachable from the start state. And the language is clearly the empty set because there's no way to ever accept anything. So how do we solve this? Well, if you put on your algorithm hat, here all that we're asking is there a path from the start state to any final states? And you can use any graph traversal algorithm you want, because the graph here is finite. The quote-unquote DFA slash graph here is finite. So what we can do here is on input M, so remember, the eDFA problem always expects a single machine and nothing else. I keep reiterating that because having these input ideas right now is actually important later. So on input M, where M is a DFA, so that's pretty similar. What we do is treat M's transitions and states as a directed graph. If you don't happen to not know what a directed graph is, that just means a graph with directions on the edges. So you could have, for example, something like this, but without the reverse happening. So that might be possible. And then what we do here is just test if there exists a path from M's start state to any final state. Okay, so let's see. Then if there is such a path, let's think. Well, if there is a path, that means that there is a way to get to the final state from the start one, which means that the machine does accept something. But the problem we're trying to answer is the emptiness problem, whether it is empty. But if there is a path, that tells us that it is not empty, which means here we should reject. If there is a path, that means that it accepts something, which means that the language is not empty. So the reason why I'm repeating that is that having that logical thinking about whether to accept or reject or do the opposite at the end is actually really important. But then otherwise, if there is no such path, that means that there is no way to accept anything, which means we should accept. Okay, and steps 1, 2, and 3 are running in a finite amount of time because, well, Step one, well, that's just going through the machine and making a graph out of the transitions in the states. Well, that takes a finite amount of time because the machine is finite to start with. For finding a path, well, we can just use breadth first search or depth first search or something and keep track of the states that we have seen and not repeat any state we've ever seen. So that runs in a finite amount of time because there are only a finite number of states. And 3 obviously runs in a finite amount of time. So we can conclude here that E sub DFA is decidable. Okay, so let's now get to, so you may think, okay, well, this is kind of a silly problem, right? What if I wanted to test whether it's a particular language like Sigma star or something? And you could do that, and there's an analogous way of doing it compared to this approach. But there's a much more important reason why we're talking about this, and that's the next class of problems, but which may seem completely unrelated, but the emptiness problem is actually very, very closely married to this problem. And that is the EQ class of problems. And by the way, you can call these languages anything you want, technically. It's just that the prefix here, like EQ and A and E, just are indicative of what the problem actually means. But you can technically call them anything you want. So the EQ here stands for the equality problem. So you may think, well, okay, well, does my DFA actually satisfy a specification? Does it actually do exactly what was asked? And that's what this problem is trying to answer. So this problem has 2 DFAs. So M1, M2 are DFAs. And the language of M1 equals the language of M2. So these 2 DFAs, although they may look completely different and have different states, different sets of final states, for example, they have exactly the same language. They accept exactly the same strings. So they do literally the same thing. Okay, so how would we actually solve this? So it's actually pretty slick how to actually show that this is decidable. So I claim that this is decidable, which is really nice. If you are unfortunate enough to be a grader for a large theory class like this one, and you want to test whether student submissions of DFAs match the instructor solution, well, that's easy. You can just run the algorithm that we're going to talk about here. And if the decider says no, then that means that the student solution does not match the instructor one. So how would we actually solve this? And the way that you should view this is look at what this is saying. So what we're trying to answer is M1, M2, so that string, the representation of those 2 DFAs, is inside EQ DFA, if and only if the language of M1 equals the language of M2. And they're DFAs, but we'll just assume they're DFAs at this point. So the answer of the question that we need to do is whether or not these 2 sets are the same. And we've done this several times at this point. How do you check whether or not 2 sets are the same? Well, what you do is you just check if one is a subset of the other and vice versa. So this is if and only if L of M1 is a subset of the other one, and L of M2 is a subset of the first one, this language. So then all that we have to do is, well, let's just solve this problem and this one. And then we just keep track of what the answer is to both of them. and output the answer, which is the AND of the two answers to this. So one way that we should view this is A is a subset of B if and only if A intersection with B complement is empty. And I think we've done an exercise on this exact thing before. So A is a subset of B. Well, that means that there's nothing in A that's not in B at the same time, which is what this is saying. So there's nothing in A that is also not in B. But we have this pesky other one that has it in both directions. So a visual way of looking at this is to make a Venn diagram. Not the best Venn diagram I've ever done, but what we can do is, let's just say that we have L of M1 be this, the left bubble, and L of M2 being the other one. And what we want to do is check if these two circles are the same. If they are the same, great. If they're not, then we report that they're not the same. Well, another way of viewing this is, let's look at these regions over here. So this region, oops, went too far, and this region. So these two regions that I'm shading, well, what property do we want these two regions to be? Well, the left one is everything that is in the first language, but not in the second one. And the one on the right is all of the strings that are in the second language, but not the first. So we want the union of these two areas to be empty. So in other words, we want both of these we want to be empty. Okay, so if one of them is not empty, then that means that one of the subset tests failed, which means that they're not equal. And if there is a string in any of these two areas, then that means that it's a string that is in one of the two languages and not the other one. So, in other words, what we want is the language of M1 intersection the complement of M2s, and then union. So this is the left area, and then the other area is language of M2 intersection the language of M1 complement, and this one here is the right area, and we want both of them to be empty. So what we're asking here is this this gigantic expression equal to the empty set? Because if it's not, then one of the two, because there's a union in between, one of the two must be non-empty, which means that the two sets are not the same. But something we should note here, well, we can actually make a DFA, or I should say this, can make a DFA for this, because it's just the intersection of two regular languages, and the one on the right has the little bar on top, while regular languages are closed under complement too. So we can make a DFA for the left half. We can make a DFA for the right half too, for the very analogous reason. And we can make a DFA for the whole expression, because there's a union of two regular languages in the middle. And let's just call the resulting DFA R. Okay, so then what we want to test is whether or not this resulting DFA has empty language. Well, thankfully enough, we've done the work already to check whether a DFA has empty language. So then ask the decider for E sub DFA on R, the string version of R. So then if the decider says, yeah, it is empty, well then that means that's exactly what we want, which means that the two DFAs have the same language. So if yes, then accept, because the language of M1 equals the language of M2. We're trying to answer the equality problem here. And then if no, then reject, because the language of M1 is not equal to the language of M2, for the reason that if it's not empty, then one of these two subsets conditions is not true, which means that there is some string that one accepts that the other one doesn't. Well, does this run in a finite amount of time? Well, the construction of the DFA part does run in a finite amount of time because it's just the product construction, which runs in a finite amount of time because we have DFAs. Each of the DFAs that we have is finite. And the gigantic DFA is a lot bigger, but again, it still runs in a finite amount of time. And we have a decider for the emptiness problem, so it runs in a finite amount of time. Therefore, after all of that, we have that EQ DFA is decidable, which is really, really cool. So what we should take from this is that A sub DFA, emptiness for DFA, EQ DFA, all decidable. And the great thing is that you're not limited to DFAs because we can just do conversions. So we could answer the exact same questions for NFAs. We could do the same thing for regular expressions, whether two regular expressions are the same is a very widely asked question. So we can answer all of those questions because we can always just do the conversion to a DFA and then just appeal to the decider for either A DFA, E DFA, or EQ DFA. So I think that's enough to cover at once. So next time we're going to start to answer questions about the context-free languages, the same types of questions. So I'll see you in the next lecture.